Hello and welcome to Infoverse Tech, and thank you for subscribing. Um, this is a channel where we explore new trends in technology, especially in the areas of big data like artificial intelligence, machine learning. We've also done some work on Python, and today we're covering the second part of Julia, where we did earlier introduction to Julia mathematical operations. Today we're going to look at some a little more complex mathematical operations, which are perhaps unique to Julia, like rational numbers and power functions. So let's get started. Let's just dive in. As you can see, I'm using Jupyter Notebook. I highly recommend this platform. It allows us to easily add code, make corrections, and also be able to share our code. And at the same time, it's really pleasing to look at. So highly recommend it. So the first function that we're going to look at are trigonometric functions. So the sine, cosine, tangent, and so on. Now the thing to note here is that if I want to find sine of 30, this is actually the 30 is treated as radians. So we need to, if you're more attuned to understanding in the form of degrees, we need to do a little conversion. So that's a very simple conversion, and I can just show you how that's done, and we can apply that to any number that we need to be converted as radian. So I'm just keeping it in a variable called d30r for easily identifying it, and what's happening is 30, and that's your degrees, into pi divided by 180 will give you the required radian value. So let's run that. So that value is stored. Now if I do sine and I want to find sine 30, I'm going to use this variable. This makes it easier, and when I run that, you can see our expected value was 0.5, but this is Julia, so it really approximates it to many decimal numbers, but again it's very close to 0.5, which is the required value. So similarly you can run it for another like cosine or sine, and again the concepts are the same. What we can do is let me change this to 45 if I'm looking for, and move this into a variable called d45r. I'll run that. Let me run. So I'm looking for cos 45 degrees. Let's run that, and again the answer is consistent with our findings. So you can apply it to cotangent, tangent, secant and cosecant, all the trigonometric functions that we are very well aware. Now there's also you can use degrees directly, and the way to do that is to use d at the end. So if I use sine d and just enter like 30 and run that, I should get the answer which is matching what we got earlier as well. Similarly I can do cos d 45, so it'll take degrees directly, and when I run that again I get the number that's consistent with my previous result. Now let's look at some an additional one. So calculating the hypotenuse, it's a very common requirement in trigonometry to calculate the third side, especially if it's a right angle triangle. So Julia provides a function called hypot, and you just plug in the values. So two unknowns that it requires. So let's say I want to find out one side is 3, the other side is 4, so it should calculate the hypotenuse, and that we know should be 5, because that's a square plus b square equals to c square, and when you take the square root it should give you the correct answer. So when I run that I get 5. So very convenient way to find the hypotenuse of a right angle triangle. Now let's look at rational numbers. Now rational numbers are any numbers that can be written as a fraction with integers, and I'm just pasting the definition here. So any number that can be written as a fraction with integers, and it's called rational number, and Julia really provides a very unique way of representing that. So let me write something like let's say, and let me show you the syntax first. So rational 4 by 7, and do note that the R is uppercase, otherwise you'll run into an error. When I run that, it gives me 4/7, and the way of representing it is with 2 slashes. Now let's do something like 3 and 9 rational, and when we run that, it actually simplifies it to the lowest form, which is very pretty unique and interesting, that we know 3/9 is actually 1/3, so it automatically reduces it to the most basic form. So very interesting. Let's run that again with and just add another number, like let's say 4, and see how it responds to that. And you can see that it actually calculated the correct number and gave us 13/3. Now when we add something like a floating point number to this, it is no longer a rational number but becomes a real number. And let's see, when we run that again, and instead of giving you like in a fraction format, it gives you as a real number. So again, pretty smart of Julia to handle that automatically. We can also handle imaginary numbers, so let me write a number here and see how Julia will handle that. And when I run that, it actually gives me the rational with the imaginary number included. So pretty smart how Julia handles this. Let me add a little more slightly complex number, and we see that Julia handles it very well. It it calculates the real number, because we've added a real number at the end, and still calculates includes the imaginary number. Now it also provides some way to identify the numerator of any fraction. So if I run this, it will correctly identify 2 as the numerator here. Similarly, I can repeat with another number and note how the result will be, because if you remember, Julia will any fraction can bring it down to the most basic level. So here we know that it's going to be 1/2. So let's see what Julia prints out, and you can see correctly that the numerator is actually 1/2, and numerator it correctly identifies as 1. We can also use something similar, which is denominator, and let's see how Julia handles that, and it'll tell you that 5 is the denominator, which is correct. And we looked at hypotenuse earlier, and there's a slight modification to that when using fractional numbers, rational numbers, and you can actually use them here, and it will calculate the correct number or hypotenuse value for you. So I found this very interesting, and the way Julia represents this, and I'm sure most of you will find it useful in your calculations as well. Now let's look at some power functions, and the first one that we're going to look at is what is called is power 2, and this function actually determines if the number in the brackets is a power of 2 or not, and we do know that 8 is 2 to the power 3. So that's when we run that, it actually says true. So the result is Boolean. It'll give you true or false. Let's look at another number. So here, instead of 8, let me say 18, and we know that it's not a power of 2. 16 is. The next one would be 20, but not 18. So it should give us a false, right? And in fact, I'm sorry, when I said 20 is not a power of 2. In fact 24 is, so we can just double check that here. So again, very innovative way to find that out. Let's look at the another number, which is so you can also use fractional numbers here. So if I write is power 2 and I use fractional numbers, and we see how that, so again it's true because we know that 8 is power of 2. Okay, let's look at some other functions, again very unique to Julia, something called next power, and this basically means it's an inbuilt function in Julia which is used to return the smallest, a to the power n, not less than x, which is the number here, where n is a non-negative number and a must be greater than 1. So if I actually include the syntax we're talking about, so let's say a to the power 7, and when I run that, so the next power, it can't be equal or less than this, so it's going to be the next power, which is 8, and again it is correct. Let's look at some other example with let's say for 3 and 9. So now 9 we know is the power of 3, so let's see how the result is, and it does say so it has to be equal or greater, it can't be less than this number. So again the closest is 9 itself. Let's look at one more example. So in this case we'll take 4, and I'm looking at 15, and let's see what Julia responds with. So 16, so next power is 16. So again very interesting function that I'm sure will find a lot of use when you're doing some calculations. We also have what is called power mod, and this, as the name indicates, is actually a combination of taking a power and also doing like a modulus on that number. So here you're raising 2 to the power 6 and then taking modulus 5. So we know 2 to the power 6 is 64, and it is equally divided by 5, so 5 does go into 60th and the remainder is 4, so you get that answer. So another way to really write this is to drop the power and just use 2 to the power 6 for the same function, and you should get the same answer. So two ways of representing that, and you can have other examples, and you should get the same results. Okay, let's look at some matrix operations. Like I said, this is a short continuation of the previous video, and I just wanted to cover some of the mathematical identities and operations which we will come across and which we will use in Julia. So let's look at the matrix operations. Now they do provide something called zeros, and this will actually write everything as the name suggests, fill out the matrix with zeros. So if I do a 2 by 2 matrix and run that, it creates a 2 by 2 matrix and fills it up with zeros. Similarly, I can do ones and with the same result. Let's do trues. So here I can fill it with, and let's make it a little bit bigger matrix, the 4 by 4. So here it'll fill it with ones which are true, and again I can replace this with falses, and it should fill it with zeros, indicating that the result is false. We also have a random n, and this will generate an array of a uniformly distributed random numbers in a certain interval, which is 0, 1. And let me just write it down. So it'll be in the interval 0 to 1. Now let me do 4 by 4. So I should get a 4 by 4 array, and you can see it generates. So Well, this I've seen something similar in other languages as well, not very unique to Julia, but again, a very handy way to quickly calculate a large matrix of random numbers. We also have random n, and as per the definition, I can just paste it here. This is an array of n normally distributed random numbers, which means that the data around the mean occurs more frequently. So let's do a 4 by 4, and you'll immediately see that it's different than the random one that we generated earlier on. So again, a quick way to generate normally distributed random numbers. We also have a way to fill. So fill 5 by 3, and it'll just fill it with the number designated, which is 3. So when we run that, so it creates a 3-element vector and it fills it with 5s. And let's say I want a multi-dimensional, so I can write the same one, but in this case I want 5, and I want an array of, let's say, 4 by 4. And when I run that, this is going to create a matrix of filling it with 5, and it's a 4 by 4. So again, very smart way to fill out a matrix with certain numbers that you require. So that was all that I wanted to cover, and stay tuned for more videos on Julia and other technologies, and thank you once again for subscribing.